So it's welcome to the afternoon session. It's a great pleasure to be introducing Todd Kemp from San Diego, who will speak about the free zero bias.
Thank you, Dima, and thank you for this invitation. And I'm really very sad that I'm not there with all of you. I'm on the mend from whatever I've been sick with for the last 2 weeks, which I've been affectionately calling FOVID because I've been testing negative for COVID, but otherwise had all the symptoms that prevented me from being there with you guys. I want to tell you today about a fun project I've been working on for a couple of years with my friend and colleague Larry Goldstein from USC. This is a meeting on free probability, and we all know that over the last decade and a half, there's been a lot of development in non-commutative analysis, maybe free analysis, we could call it. I'm hoping this is the first talk that you've seen on what might be called free statistics. But we'll see if we can agree that this is a move in that direction. Because the difference between probability and statistics has everything to do with empiricism. And this was today's XKCD comment, which I thought was quite relevant to the question at hand, because I'm going to talk a lot today about sampling and bias and how we can deal with some of those things. So I'm going to start with a fun sort of thought experiment. It's a thought experiment because of modern technology, which is different from when this experiment might have taken place. Back in the day, here in the US, or I guess nowadays in Canada, where most people still have landlines, it was at one point common for households to have many landlines. When I was growing up, our house had 4 landlines at one point. There was the main landline for the house. Both my brother and I, when we were teenagers, had our own landlines, and there was a dedicated landline for the internet as well. You could have another one for a fax machine. So the phone company, of course, would have records of how many landlines each household had. But suppose that a consumer advocacy company wanted to get a sense of what's the distribution of landlines per house. How would they figure that out? Well, they could take the phone book and they could call a representative sample of telephone numbers from that phone book. And when people answer, ask the question, how many landlines do you have? And then plot a histogram of that data. So that would be one way to try to figure out the distribution of landlines. So here's a question for you. If you do that experiment and then you plot that histogram, is that histogram the histogram of number of landlines? If X is the random variable number of landlines per house, is the histogram different?
I'll answer for the room. It's the number of landlines per landline. It's the number of landlines in the household of the landline, right? So of the line you called.
Yeah, so I mean, you're pointing out that there is a confirmation bias involved here, right? And another way to think about why this is not representing the right data is how many people, when you call them up, are going to answer, oh, I don't have any landlines? I mean, these days, you might have called a cell phone, but back in the time of landlines, of course, you are excluding from this sample anyone who doesn't have one at all. But also, in a household that has 4 or 5 landlines, all of which could be answered by a human, they are getting overrepresented in the sample. So you have a bias.
Fax machines.
Yeah, well, I don't know about you, but our fax machine, we were constantly, picking up the wrong phone and hearing ding. So that could still happen. Now, this might sound like a funny, contrived example, but a more modern and continuing example where this exact same thing happens is if you look at data of the sizes of oil wells that are mined, it looks like larger oil wells are much more common than smaller ones. But that's just an example of the same kind of bias. It's easier to find the larger ones. So what we're seeing here is an example of what's called size bias. If you have a distribution X, then what we're actually sampling there is the size bias of X. I'm going to be very fluid in this talk, going between distributions of random variables and random variables themselves. So I'm going to talk about the size bias of a random variable. What I really mean is the size bias of its distribution, but I'll talk about a new random variable that is the size bias of the old one. It's only defined up to its distribution. So here's the formula. Here's what we're getting. The size bias of a distribution is the new distribution whose Radon-Nikodym derivative with respect to the old one is x divided by the mean. This only makes sense if you have a positive random variable with a strictly positive mean, okay? And that's the case for the examples we were just considering. So that's the size bias distribution. A better way to understand it and to work with it is through the following functional equation. If you have a random variable x, its size bias is given by this functional equation here. You can all see my mouse on the screen, I hope. Great.
Yes.
Right. So the expectation of f at x for any sufficiently nice test function f is given by the mean times the expectation of f at the size bias of the random variable. And you can see from here that you can, in fact, recover the original distribution from the size bias distribution, except what you lose is the information of any mass at zero. Of course, you can't recover that. You don't know how many people would have answered the phone saying, I don't have a phone. That's not possible. But up to this point mass at zero, from this, you can, divide through by x inside, and you can recover the original distribution other than the point mass at zero. Okay, so that's the size bias. And I want to tell you about a couple of properties that it has, just as a warm-up here. So if you have a bunch of independent samples, if you have x1 through xn are independent non-negative random variables, all with positive means, and you look at their sum, how might the size bias of the sum relate to the size biases of the individual random variables? You might naively hope that size bias is sort of linear or independently linear anyway, but it is not. Instead, what you have is the following exchange property. If you take a random index between 1 and n, which is chosen independently from the samples, from the x1 through xn, and chosen with distribution proportional to the means, like this, then what you do is you take the sum and you swap out the random index random variable and put in the size bias one. And that is the distribution of the size bias of the sum. If your variables were identically distributed to start with, you don't need to choose a random index. You could just choose the first one or the seventh one, whatever you want. So this is maybe a little easier to understand. The size bias of the independent sum is, you size bias one of the variables and add it to the others, where you've now coupled this size bias random variable to be independent from the other ones as well. So that's the exchange property or the swap in property for size bias. Now, one could ask, for example, okay, maybe the distribution that I got for the landlines wasn't so off. Maybe the size bias distribution was pretty close to the actual distribution. That's actually probably true. Well, not quite. It's a little shifted. What we're asking is, I guess, what distribution might be a fixed point for the size bias transform? Well, if you write out what it means this here, and you can see right away that, well, one way you could get a fixed point here, you could get this equality, is if x is just equal to m, if x is just constant. And in fact, that is the only fixed point of the size bias transform. But so that's if everybody has just one landline. But what if you allow for a shift as well? So consider this transform here. You take a random variable, you size bias it, and then you subtract 1. Does that have any fixed points? Well, here's an exercise. The unique fixed point distribution for this shifted size bias is the classical Poisson distribution with mean m. Okay. Now, this is not the right way to prove this, but you should just write down from the functional equation, what does this mean, the fixed point of this transform? It means you're trying to find, for all sufficiently nice functions, f, a distribution x that has this property here. And if you write down what that says about moments, this is a free probability meeting, we're all fond of moments, then you quickly set up a recursion for the moments here, and you recover the moments of a Poisson distribution. So at least this shows us a unique fixed point among those distributions determined by their moments. Okay, so that was just a warm-up about one particular kind of bias distribution. I'm interested in, free versions of these sort of things. So we might ask, is there a free size bias? Of course, that might only be interesting if we could talk about size bias in a multivariate context, which is actually quite challenging. The size bias of a distribution is just a transform on a probability measure, so it's not quite clear how freeness would come in. But you could ask a few questions. You could ask, is it true? So maybe the free size bias is just the size bias. Maybe there isn't a difference free size bias. But you might want to be true in that case, this exchange property holding in the case of free sums. Suppose I have freely independent random variables, I add them up in size bias. Should I get the same thing if I size bias only one of them and add up the free sum of those guys? Okay. Well, that's definitely not true for the classical size bias, and you can check it with two shifted semicircular random variables and compute it explicitly and see that it's just not true. Okay, so maybe there is a free size bias that we could find somehow that does have this property, or maybe it should have as a fixed point the free Poisson distribution. So these are interesting questions that we've thought about a bit, and we have some ruminations on, but certainly nothing ready for the light of day just yet. Instead, I want to tell you about a different kind of bias, one that would work for mean zero random variables where size bias doesn't make sense. And to get there, I'm actually going to start talking a little bit about Gaussian integration by parts and Stein's method. So if you have a standard, or not standard, if you have a centered semicircular random variable, I'm not seeing a clock, so I better make sure I'm not going way over time. There we go. If you have a standard, a semicircular random variable that's centered and variance t, then an integration by parts formula that dates from the 19th century or earlier says that, if I take the expectation of z f at z for a nice function f, that's the same thing as the expectation of f prime at z times the standard deviation, or times the variance t. Okay. And actually, this uniquely specifies this distribution, the normal distribution, as you can easily check. If you let f run over convex supported smooth functions, for example, that's enough to recover this. In fact, if you take f to be a polynomial, this is enough to recover the Gaussian as well by another moment recursion calculation, if you like. So this is actually a starting point for what's called Stein's method. The extent to which a random variables distribution fails to satisfy this equality in different ways of measuring that failure, that set of tools is generally called Stein's method. And those tools can be extremely productive in providing sharp estimates in normal approximation schemes like central limit theorems. So there's way too much to say in this short time to describe Stein's method in general, but I'll just mention one thing that has some contact with free probability, thanks to some of the people in the room there, Stein kernels. So if x is a real-valued random variable, then we say it possesses a Stein kernel A, which is a function of one variable in this one variable context. If for all nice functions f, the expectation of x f at x is given by what you would hope to find in the Gaussian integration by parts formula, expectation of f prime at x, but instead of just times a number, the variance, we put another function inside of x, a of x. So there's our Stein kernel. Okay. So of course, if x is a normal of variance t, then it possesses the Stein kernel constant, a is equal to t. And so that means that one way you could try to measure distance or difference from a Gaussian is by how big the derivatives of this putative Stein kernel are. If they're far away from zero, then your distribution is far away from a Gaussian. So that leads to one of many definitions of Stein discrepancy, which can be used to provide sharp L2 Wasserstein estimates on the distance to a Gaussian. and Brent Nelson and Ian Charlesworth and others have used this idea imported into the free probability world to provide some very interesting tools in the Lanham and algebra's context that I'm not going to try to touch at all. But this does make contact with that, and we're going to come back to Stein kernels a little later. Now, in the classical context here, Stein kernels are always unique, but they don't always exist. Some distributions don't have Stein kernels. If you have one, there's only one. Characterizing those distributions that have a Stein kernel is actually a very difficult problem, even in one dimension and certainly in higher dimensions. The one existence theorem that I'll mention here, and I'll show you how to prove it using bias in a moment, is that if you have a distribution with mean 0 and it's absolutely continuous, it has a density, and its support is connected. Okay, so if the density is fully supported on its interval of support, then there is a Stein kernel, and you can give an explicit formula for it. Here it is. Okay, so I guess as an ansatz, you can just write this down and check that that's a Stein kernel, and there's a proof. But where did this come from? Well, now let me tell you where it came from and connect all the things that I've mentioned so far. So Stein kernels I just introduced as one way to deform the Stein equation, or the Gaussian integration by parts formula. Instead of just a constant t, we have this kernel there. But there's a different way to deform this equation, which relates to the size bias. Here's the size bias equation that I wrote before. And all these things have the same expression on the left, expectation of x f at x. Okay, so this one has an f on the right. These ones have f prime on the right. So let's combine those two. And let's ask about a new distribution, which I'll call x star. It's going to be called the zero bias distribution. We'd like to find for a given random variable x, a distribution x star, which has the property that for all nice functions, the left-hand side is equal to some constant we might need, times the expectation of f prime of this new variable x star. Okay, so you can check by taking f to be a constant or f to be the identity function that, first of all, for this to make any sense, the random variable had better be centered, and that the constant, if it's going to work at all, has to be the variance of x. Okay, well, that functional equation there defines what's called the zero bias transform. Again, it's just really acting on the distribution. And it is, in fact, well defined on the set of probability distributions on the real line with mean 0 and variance t. There are several different ways to construct it. And as we can see from the start point of this discussion, the normal of variance t is the unique fixed point of the zero bias distribution. So I'm going to show you one construction right now that will be relevant to our discussion in a few minutes. And this is a nice probabilistic construction. There are also analytic constructions. And it involves yet another bias, kind of bias. So if x is a non-constant L2 random variable, its square bias is very similar to its size bias. Instead of biasing by the size, you bias by the square of the size. In other words, you're just doing the size bias twice. And the associated functional equation for that is given here. Instead of xf at x on the left, it's x squared f at x. So this is a typo. There should be no f here. It should just be expectation of x squared f at x on the left. And on the right here, we have up to the variance, the expectation of f of this new bias distribution, the square bias. So here's the construction of size bias. If x is a mean 0 and finite second moment random variable, then if we square bias it and then multiply it by an independent uniform random variable, the resulting distribution is this zero bias. Okay? And this is now, once you know this, this is just a calculation that you can do. You can give this as an exercise to your undergraduate probability, your good undergraduate probability students, and check it. Okay? So that's one nice construction of zero bias from other biases. And here are some properties of this zero bias distribution. Okay, as I just said, it's well defined. It is multiplicatively linear. If you multiply your random variable by a constant, that's the same as multiplying its zero bias by that constant. It's robust under weak convergence. If Xn is a sequence of mean zero random variables in L2 that converge to a mean zero random variable, and if the variances also converge, then the zero biases converge in distribution. The distribution of the zero bias is always absolutely continuous. No matter how rough the initial distribution is, you zero bias it, it now has a density. And the support of that density is equal to the convex hull of the support of the original. It can fill in holes in the distribution, okay, but it always goes edge to edge. So it's always got connected support. Now, because of the relationship between the size bias and the square bias and the size and the zero bias, the zero bias, the size bias, and the square bias, which those relations, you have a similar independent sum exchange property for the zero bias. And it looks just like the one that I gave for the size bias, except now you have to weight the random indices by the variances instead of by the means. But if we just consider the IID case again, and then it's the same as before. If you take an independent sum of random variables and zero bias the sum, so they're mean zero random variables, that's the same as just picking any one of them and zero biasing it, and then adding that independently to the others. This is a very useful property because of the relation between zero bias and Stein's method. This means zero bias can be used to provide very slick proofs of Berriosine theorems for central limit, for the central limit theorem, for example, which I will not have time to talk about here, but would love to. Let me tell you about now the connection to the Stein kernel that I mentioned before. So here's again the definition of the zero bias, the zero bias defining equation. And I'm going to use this to show you how to construct the Stein kernel in a case where it exists. So I'll just use the change of variables formula here to say, oh, well, this is just given by integrating f prime against the law of mu star. And as I just mentioned a moment ago, mu star always has a density. Now, suppose that the original X also has a density, and that density didn't have any holes in its support. Suppose that it was supported on the full interior of its support. In that case, from the theorem I mentioned on the last slide, the supports of mu and mu star are equal. These are equivalent measures. And I can just divide out by that density rho x and multiply by it again. And, oh, there's my Stein kernel. Okay, I think I lost a t from this line to here, but this shows that under these assumptions, I can take the ratio of the densities of the zero bias and the original distribution times the variance of the original distribution, and that's the Stein kernel. Okay, so this shows that if you have a density with full support, you have a Stein kernel, and the uniqueness theorem says that's the Stein kernel. More generally, this argument works whenever the original distribution is absolutely continuous with respect to the zero bias distribution, which is more general, when these are equivalent to each other. Okay, so that's actually pretty much the state of the art as far as I know, and when a Stein kernel exists in one dimension using the zero bias. Now, let me mention some very recent work of my co-author, Larry Goldstein, and his co-author, Schmoke, on connections between zero bias and infinite divisibility. This is classical infinite divisibility. So just a reminder of definitions. A distribution is infinitely divisible if, for every n, you can represent it as a sum of n IID random variables. Okay. In this ongoing work of Larry and Yuval Schmoke, they prove the following really interesting result. In order to state it more fully here, we need to sort of extend the zero bias beyond the mean zero context. And one sort of naive way to do that is to just, if I've got a random variable, I'll center it, take the zero bias, and then add back in the original mean. So that's the distribution. That's the transform we're going to use here. So the theorem is as follows. Random variable x is infinitely divisible if and only if there exists another random variable, distribution y, such that if I realize x and y independently and a third uniform random variable independently of those, then this shift and shift back zero bias is equal in distribution to the original random variable plus u times y. Okay. So I'm going to, on the next slide, tell a little more detail about this. There was some slightly earlier work of Arras and Outret that relates to this, so I don't want to miss out giving credit where some credit is deserved. It relates to the Kolmogorov's theorem on the Levy-Khinchin representation of infinite divisibility. I should mention here that all of this requires a second moment to be finite. So here's the Levy-Khinchin formula for infinitely divisible distributions, which is called which is due to Kolmogorov. Not sure why it's called Levy-Khinchin. I guess they all must have contributed. So if you have an L2 random variable with variance sigma squared, it is classically infinitely divisible if and only if its classical cumulant generating function, that is the log of its Fourier transform, has the following representation. Okay, other than a point mass at 0, it's given by this integral of this modified exponential here against some probability measure. Sometimes this is stated with the sigma squared combined with the probability measure, and it's just a finite measure in that case, but I like to call it a probability measure. This is antiquity we're talking about here, this early 20th century result. What Goldstein and Schmuck proved is that this identity, this zero bias identity, holds if and only if this holds true. And that holds if and only if the variables are classically infinitely divisible. All of those are proven together by them. And what's really interesting about this, aside from it being a totally new proof of Levy-Khinchin formula, is that it gives probabilistic meaning to this Levy-Khinchin measure nu. The Levy-Khinchin measure nu that appears in this formula is the distribution of y. Okay, so what that measure is the up to this uniform smoothing. It is the defect, the x star minus x defect. How different is x from its zero bias? Just like we were talking about how different is a distribution from its size bias before. That's what the Levy-Khinchin measure measures. Okay, so my time is a little more than half up, and I'm halfway through my slides, so I'm doing well. I would now like to talk about liberating everything that I just described. So I'd like to tell you about a theory of free zero bias, or at least as far as we have developed so far. So to start, I want to remind or tell everyone about non-commutative derivatives that come up in free probability. So in non-commutative probability in general, we usually like to let single variable functions do double duty and act on operators as well. You heard a lot about this from my colleagues, Vaki and David, talking about our project on non-commutative stochastic calculus. So when you do this functional calculus double duty, functions that are smooth as a function of one variable may or may not be smooth, depending on what you mean by smooth, as operator functions, because the relationship between derivatives in the two contexts is fairly complicated. But if you're smooth enough, it will work. So in the simple case where, say, you have a polynomial of one variable, then if you view that function as a functional calculus function acting on a C-star algebra, it is a smooth function in the classical Frechet sense. And we have this relationship between the derivatives, the usual Frechet derivative, the directional derivative of the functional calculus polynomial function at a point A in the C-star algebra in the direction H in the C-star algebra is given by this free difference quotient hashed with the direction H. Okay, so this hash is just, this free difference quotient is something that maps the C-star algebra into its tensor product with itself. And the hash is this operation that takes a tensor product of two things and puts them on either side of the direction H. And the free difference quotient del P is defined like this, okay? But a much more intuitive way to understand it is to say, well, this takes values in, really this formula says that the output is a tensor product of two polynomials, or is living in the tensor product of single variable polynomials with itself. And that is canonically identified with the space of polynomials in two variables. So if we make that identification, then what this really defines is this del P is a polynomial in two variables, and it's just the difference quotient. Okay? So free difference quotient is, in this context, at least in this simple one variable context, can really just be thought of as the difference quotient. Now, I want to get back to the Stein equation that we mentioned before, okay, which uniquely specifies the Gaussian distribution. So now that we know what kind of non-commutative derivative is likely to come up in a free context, there's a sort of low-hanging fruit modification we could make to this equation to liberate it. And that would be the following. We'd like to look for a distribution S around a variable S, which satisfies this equation with the f prime replaced with del f. Now, del f takes values in the tensor product, so we're going to have to replace the expectation with the tensor product expectation here. Maybe in this room, people would be more comfortable if I called this tau instead of E. I really think we should all be using E for tau. It's just expectation. But that may be a controversial statement. So viewing del as really just the difference quotient, we could rewrite this equation here like this. And because this is tensor product state, that really means we're talking about classically independent copies here. So this free Stein equation says, oh, expectation of SF at S should be the variance times expectation of the difference quotient of F at two classically independent copies of this unknown distribution S and S prime. Okay. So here's a nice exercise that I calculated when I was a postdoc, I remember, and I'm sure other people have done it before. The unique solution in distribution to this equation is the centered semicircle of variance T. And since every talk should contain one proof, I guess, here's the elementary proof of this. First, let's just take T equal to 1. You can renormalize that away very easily. And let's take our functions f to be monomials. If you write out what this says, then on the left, the expectation of f at S is the k plus 1th moment. And on the right, we get this sum of products of moments. Okay. Now, notice that because of parity considerations here, if k is even, so that this is an odd moment on this side, every one of these terms will contain one of these being odd. And we started with the assumption needed for the free, if we start with the assumption, which we need to for this equation to make sense, that the expectation is 0, then a recursion of this quickly shows you that all the odd moments are 0. And then for the even moments, if we take k to be odd, so that the left-hand side is even, this just says the following here. And if we now eliminate the odd moment terms from there that we know are all 0, we get this equation here. And this is exactly the Catalan recurrence. And that shows you that the moments of this putative distribution are the Catalan numbers. The even moments are the Catalan numbers, ergo the semicircle is the solution. Okay, so that's the solution of the free Stein equation. So now let's modify it. One way to modify it would be with free Stein kernels, but now we have this zero bias motivating us. Let's modify it to define a free zero bias. So putatively, the free zero bias of a distribution is a new random variable, a new distribution, which is defined by this equation for all sufficiently nice f. Okay? And again, if you don't like dealing with tensor products and the full definition of the free difference quotient for polynomials, if you'd like to be able to easily make sense of this for more general f, in this simple one variable context, we can just take that to be the actual difference quotient. So that is, we're looking for a distribution which, when we take two independent copies of that random variable, x circ and y circ, we get this here. We want to sub that into the right-hand side. If you don't like dividing by this difference of two independent random variables that we don't know the distribution of, I don't, you don't actually need to worry, because there's this nice integral representation of the difference quotient. It's the expectation of the derivative of f at this interpolation by an independent, by a uniform random variable and its reverse, which is another uniform random variable. So here's an equivalent statement of the putative definition of the free zero bias, which will make perfect sense as long as f and its derivative are integrable enough. For example, smooth convex supported functions. This certainly makes sense. That doesn't mean that we've shown that it exists, but this equation makes sense. And by the way, if you compare this to the definition of the zero bias, the classical zero bias, this shows that there's this nice quadratic relationship between the free zero bias and the classical zero bias. That is, if we could calculate, if we knew what the zero bias was, we could get the classical zero bias from it. We take two classically independent copies of the free zero bias and an independent uniform random variable and take this interpolation, and that gives us the classical zero bias. So that means that since we know how to construct the classical one, if we want to construct the free one, we're probably going to need to solve some kind of functional quadratic equation. So let me show you one way to do that. Let's just take our test functions to be resolvents. And a nice little quick calculation here shows that the difference quotient of this resolvent function is the product of two resolvent functions. Ultimately, I think this is why Cauchy transforms are so useful in free probability. So if we plug this into the defining equation that I wrote for the free zero bias, it gives you the following quadratic equation relating the Cauchy transform of the original random variable and its putative free zero bias. So if we want to see that the free zero bias exists, all we need to see is that I can take the square root on the right-hand side here and get something that is a Cauchy transform. That is, given a Cauchy transform of a distribution with mean 0 and variance t, if I take zg minus 1 divided by the variance t, is the square root of that, does that have a square root that is a Cauchy transform? Well, once you know that's the right question, it just takes you a few hours to realize that the answer is yes and to figure out why it's true. And for those of you who work with Cauchy transforms, many experts in the room, you probably will be able to figure that out much faster than we did. But the answer is yes, and so the free zero bias exists. And getting from there just for these test functions to all sufficiently nice test functions is a typical kind of Steiny density argument, which you can find in our paper once it's on the archive soon. But let me actually tell you a different way, or a more general way to construct this that mirrors the construction via the probabilistic construction of the size bias using the square bias before. And it relies on this extension of the result that I just stated, which my co-author Larry Goldstein nicely formulated, which I've never seen anything like it before, but maybe some of you in this room have, and I'd love to hear if you have. It's a nice little result here. Let's take two real valued random variables, and suppose they have the property that if this quantity here, the expectation of x divided by modulus of z minus x squared, that the product of those two for the two different random variables is always non-positive in the whole upper half plane. Okay? So for example, if x and y are coupled as independent random variables in the same probability space, this would hold true if x times y is always non-positive. Under this assumption, then the geometric mean of the two Cauchy transforms, their product has an analytic square root, which is a Cauchy transform of some new probability measure. So I'm going to refer to this new probability measure, or this new random variable, by the flat operation. X flat y is a random variable whose distribution has this as its Cauchy transform. If anybody has seen something like this before or realized that it connects to monotone or other kinds of variance of free probability, which I suspect it must, I'd love to talk to you. I wish I was there to talk to you in the breaks, but I haven't found something that this exactly corresponds to in the literature yet. So here's an example. If we just take our two random variables to be constants, 1 and -1, which certainly satisfy this relationship here, then x flat y is an arcsine distributed random variable. This flat operation is robust. If xn and yn converge in distribution, then their flat converges in distribution to the flat of the limits. And we're going to use this most exclusively in the case where we take one of the random variables to be 0. Right? In that case, this condition is certainly satisfied. And so I can always take the flat of a random variable with 0. I'm going to call that new random variable x flat transform. And it's just given by this here. The Cauchy transform of x flat is the square root. These are all the usual branch cut square roots in the complex plane that you can always use here, of 1 over z times the Cauchy transform of the original random variable. Okay, so I'm going to now use that to construct the free zero bias, kind of the same way that the zero bias was constructed. Let me note that the zero bias, you can write down how its Cauchy transform works quite easily. So here's the Cauchy transform of the sorry, not the zero bias as well. We've seen that, but the square bias, here's the square bias's Cauchy transform in terms of the original. So we're going to define the free zero bias here now. And this actually makes sense even if x doesn't have mean 0, as long as it's L2, by taking the square bias. And then classically, we would multiply by an independent uniform. Here, we're going to do this flat transformation to it. So if you square bias and then flat bias it, flat it, you get the free zero bias. Okay. And if you work that out quickly, you'll see that the Cauchy transform of this thing satisfies the following quadratic equation with respect to the original x. And in the special case where the mean is 0, that's the equation that we derived before. So this does construct the free zero bias. So we now have this transform, the free version of the zero bias transform. It satisfies our putative functional equation, replacing the derivative with the free difference quotient. It has the semicircle law of variance T as its unique fixed point. And actually, it's quite computationally feasible. We have many examples we can compute of free zero biases. So for example, since we've now extended it beyond the mean 0 case, if you take a 2-point measure with a point mass at 0, well, as in the classical case, the zero bias and the size bias and the square bias, they all kill the mass at 0. And so does this one. It doesn't matter what the mass at 0 is. It's only what the mass elsewhere is determines what the distribution is. So the size bias of any 2-point measure is some shifted semicircle, shifted arcsine distribution. If you want, a more precise statement, in the centered case, if you take a centered 2-point mass distribution with masses at minus a and b for two positive numbers a and b, then the Cauchy transform of the free zero bias of that is given by this nice formula here. So in particular, if you take a and b to be 1, where your x is a Rademacher distribution, then that says that the free zero bias is arcsine distributed. And we can do it again. We can compute the free zero bias of the arcsine distribution, and there is the result. It has a density, and it's not that complicated. And I think we could do it again, but not right now. So we can compute many examples, and we have them in the paper. So now as we're getting towards the end of the talk here, I want to tell you some of the nice properties of this distribution and why, of this transform, the free zero bias, and why we're excited about it. So first, here's a theorem. As with its classical counterpart, if you have any mean 0 L2 random variable, its free zero bias distribution is absolutely continuous. It has a density. And in fact, we have this nice quantitative bound on the probability measure, which tells you the usual kind of things about what happens to that density at the edge. It can have, a square root type singularity at the edge. Moreover, we can also prove that the free zero bias support is, as in the classical case, contained in the convex hull of the support of the original measure. The proofs of these facts use that nice relationship, quadratic relationship between the size bias and between the zero bias and the free zero bias, together with several nice integral representations of free difference quotients. But there is one interesting difference between the classical and the free case. In the classical case, the support of the size bias was always connected, and that's not true for the free size bias, for the free zero bias. I keep mixing up the word size and free and zero. So for the free zero bias, the support can be disconnected, and in fact, we have an exact characterization of the support sets for free zero biases of all finitely supported distributions. If you have any finitely supported distribution, its size bias has a nice continuous density, which is supported on a disjoint union of intervals, which have endpoints chosen from the original point mass points and the zeros of the Cauchy transform of the original distribution. And we can write it down all quite explicitly, we do in the paper. So that is different from the classical case. It also means that using free zero biases to construct free Stein kernels is a little more fraught, although it's still feasible. If I have time, I'll tell you about it. The free zero bias has the same kinds of regularity properties that the classical zero bias and size bias and square bias do. So that is to say, we can Steinify and extend the test functions way beyond the resolvent functions. We can use any C1 bounded functions and get that this functional equation holds for the free zero bias. It is multiplicatively linear. It respects convergence and distribution as long as you also have independently convergence of the variances, and that the limit is not a point mass. The limit is a point mass, things can go wrong. Okay, but otherwise you get robustness under convergence and distribution. And also uniqueness. Well, it can't be that the size bias determines the original distribution, that the free zero bias determines the original distribution. As we've noted, it kills any point mass at zero, but that's the only defect. If you have two random variables and their free zero biases are equal in distribution, then it follows that their square biases are equal in distribution, which means that up to a missing point mass at zero, they are the same. However, that free sum exchange property that was so useful for the zero bias in its relation to Stein's method, that does not seem to hold here. That is to say, if we take this free zero bias of a sum of two free random variables, it does not seem to be true that that's the same as free zero biasing one of them and freely adding it to the other. Now, when I say it doesn't seem to be true, I don't actually know if this is true. We worked hard to try to find a counterexample, and we're never able to find one. But there's just no reason to think it's true based on our calculations. So I don't think it's true. But there is an analog that I'll now tell you about as we segue towards discussion of conditioning and free infinite divisibility to the last big theorem. So to get there, I need to remind you or tell you about some analytic transforms that come up frequently in free probability, especially from the early days of free probability. So we've already been working a lot with Cauchy transforms. And by the way, all of our distributions here, there's no reason for them to be compactly supported. Everything I've been talking about is for distributions that might not be compactly supported. So that means things get a little bit hairy. Cauchy transforms are typically univalent far away from zero. They are analytically invertible, But if you aren't compactly supported, then the region on which they're analytically invertible isn't just a neighborhood of infinity, it has to be a Stolz angle region. So you have to cut out not just a ball at infinity, but also an angle away from the real line. But on such a region, you can take the inverse, and then you can define the R transform, which is the inverse of the Cauchy transform, minus 1 over Z. And then actually this is defined not just in the image of the Stolz region, but really in a neighborhood of 0. And then two versions of the Cauchy transform, the R transform, that come up a lot are the reciprocal Cauchy transform and the Voiculescu transform, which predates the R transform in Voiculescu's work, which is just, in this context, the R transform at 1 over Z. So I'll use all 4 of these in the coming. And then there's one more very important kind of function that comes up, which is the subordinator, another analytic function, which putatively is defined like this. So you take two distributions, mu and nu, take their free convolution, free additive convolution, the Cauchy transform of that, and then compose with the inverse of the Cauchy transform of mu. As stated, this is only going to be defined on some Stolz angle region, but actually Bian showed that this, if I move the g to the other side and write this defining equation for the subordinator function omega, it actually defines it as an analytic function in the upper half plane. And something that's important in our work, that we use in our work, which is a fact that doesn't seem to appear in the literature, but if I'm wrong about that, I'd love to hear it, that the subordinator is robust under convergence and distribution. That is, if mu-n converges to mu and mu-n converges to nu in distribution, then the subordinator of mu-n and nu-n converges uniformly on compact subsets to the subordinator of mu and nu. If Ping Zhang is there, I bet he knew this already, but I could not find this anywhere in the literature. So I'd like to thank Qingwei Ho, my former student, for sending me a proof of this using Dengye-Wolf theory that he's so fond of. In our paper, where we only need to prove this in the special case where mu-n free sum nu-n is constant, we give a much more elementary proof of this robustness result there. So where this subordinator comes up, at least for our calculations, is in conditional expectation, that is free conditional expectation. So this is the famous formula that Bian proved in 1997, stated in the special case of this resolvent function again. So if I have two freely independent random variables, x and y, then the resolvent function at their sum, if we take the conditional expectation of that onto x, we get this. We get another resolvent function, but with this subordinator instead of just z there. So we use that to prove the following, which is our version of the exchange property, the free sum exchange property for the free zero bias. If x1 through xn are freely infinitely divisible, self-adjoint centered L2 random variables, and w is their sum, how does the distribution of, how does the free zero bias of w relates to the free zero biases of the individual distributions? Well, it relates like this. The Cauchy transform of the free zero bias of w is the Cauchy transform of any one of the summands at the subordinator from one of the summands to all of the other summands together. Now, by comparison, if we write down the independent exchange property for the zero bias in terms of the classical version of the Cauchy transform, that is the Fourier transform, it says something that is quite similar, except instead of a functional composition, it's a product here. And we've all seen this before, that's how liberation works. This multiplication turns into composition involving subordinators. So this is our free sum exchange property for free zero bias. I do not think it translates into a simple sum property like this one does. Okay, so in the last moment, a couple of minutes here, I want to highlight our main theorem of this paper, which is the relationship of free zero bias to free infinite divisibility. So a distribution is freely infinitely divisible if for every n can be represented as a sum of n freely identically distributed random variables. And in the early 90s, there were two landmark papers and many others following from Harry Berkovici and Dan Voiculescu characterizing free infinite divisible distributions, again, initially for compact support and then extended beyond after that. And the first major result is that mu is freely infinitely divisible if and only if its Voiculescu transform is actually holomorphic in the entire upper half plane, not just in a neighborhood of infinity, or in a Stolz region. And then second, they prove an analog of the classical Kolmogorov-Levy-Kenshin formula for freely infinite divisible random variables, that a random variable with mean m and variance sigma squared is freely infinitely divisible if and only if its Voiculescu transform, you could write this in terms of R transform if you prefer, that's the free version of the cumulative generating function, has this integral representation, okay? Instead of an exponential modified term here, it's a Cauchy it's a resolvent again. So in other words, this happens if and only if the Voiculescu transform is a shifted and scaled Cauchy transform of some other measure, okay? Just like in the classical case, there's some mysterious probability measure here, nu, which mediates this formula. So let me now state our main theorem, which is a third leg to this equivalence. If x is a self-adjoint L2 random variable with mean m and variance sigma squared, then it is freely infinitely divisible if and only if there is some random variable y, so that the reciprocal Cauchy transform of the free zero bias of x, shifted with the mean as needed, is given by the reciprocal Cauchy transform of the flat transform of y composed with the reciprocal Cauchy transform of x. If you don't like reciprocal Cauchy transforms, you can just write it in terms of Cauchy transforms like that. Okay? And this holds if and only if the free Levy-Kenshin formula holds. And moreover, the free Levy-Kenshin measure that appears in that formula is exactly the distribution of this y. Okay? So we give probabilistic meaning, if you like, to the Levy-Kenshin measure. This is our free version of Larry and Uva's theorem in the classical case for the zero bias. Instead of this fairly simple to state relationship between x star and x in terms of a sum here, we have to state it in terms of transforms, in terms of reciprocal Cauchy transforms, but it is the same kind of theorem, and it gives meaning to the measure nu that comes up in this theorem. And I want to say that I really like this theorem for a few reasons. One is that it is a completely self-contained new proof, very different from Voiculescu and Berkovici's proof. And the other is that it, uses the free zero bias that we introduced and gives meaning to this measure nu. So let me just finish now by quickly just saying a few things that I didn't mention. That's the first thing I actually just did mention. I won't have time to talk about the relationship to Freestein kernels, but because the free zero bias always exists, we can use it to construct Freestein kernels. You do need a regularity assumption for that to work, like in the classical case. But the interesting thing is that when we do so, we construct a new Freestein kernel, which is different from any of the ones constructed before. Right? Max Fati and Brent Nelson, and then later Guillaume Sebron, together with some of the same guys and Mai, showed that Freestein kernels always exist, but they're never unique, and gave several different examples of different Freestein kernels for the same distribution. The one that we can construct using the free zero bias is a new one, not in that list before. And then finally, I'll say that a current goal for us is to try to use the free zero bias to prove sharp Berezin type estimates on quantitative semicircular approximation. But the subordination flavored replacement for the free sum exchange property is a lot more complicated than the classical one. So it makes things harder. And so we're still working on it. So stay tuned, and I hope to report on that the next time we meet. Thank you.